Well, thank you, Zvi, for that very generous introduction. Normally, when I start a talk, I would thank the organizers for inviting me here today. But since I'm one of the co-organizers, that seems a bit self-serving. So I'm going to start by thanking my co-organizers, including Zvi, Leonid, and Eric, for encouraging me to speak about Bob's contributions. Now, originally, we were going to make this a Festschrift, which means a volume of original research in honor of the honoree, Bob. And I do have a research paper on the adaptive market hypothesis that I'd be happy to contribute. So if we decide that we're going to produce such a Festschrift with some of the wonderful papers that were presented today and yesterday, I'd love to do that. But because this is the last talk, and which is always a mixed blessing, and much of what needs to be said about Bob has already been said, I thought I would take a somewhat different approach. You know, we've heard about Bob's contributions in derivatives, in policy, and in all sorts of different venues. Bob this, Bob that, Bob. I'm thinking that you're pretty tired now of talking about Bob. Even Bob may be tired about hearing about Bob. So I'm going to change the theme and talk about me. I'm going to tell you what I think of Bob. That's sort of the reverse of the typical narcissist. You know, enough about me. Let's talk about you. What do you think of me? So this is going to be the reverse. I'm going to make this a bit of a personal reflection. Like many of you, I believe I owe my career to Bob, both professionally as well as personally in the many ways that he and his entire family have supported me over the years. And I'll point out a few of those things over the course of the next half hour or so. But I'd like to make a very different point that has been made by any of the other talks. I want to talk about Bob as a financial engineer. Now, I know that that term is a somewhat loaded term these days, and I'm going to have to spend some time unpacking it and describing what I mean by a financial engineer and why financial engineering as a concept is so important for the science of finance. Well, before I do that, let me begin by telling you about myself, because this is going to be a personal view. It's not particularly learned or scholarly, but it is my view about why Bob is unique. And so I need to tell you where I'm coming from and why I think the way that I do. So I come from a family of three. I'm the youngest, older brother and sister. Grew up in New York City, immigrant family, single-parent household. And we were really focused on science and math and engineering in my household. My sister is the chair of the Department of Developmental Biology at the University of Pittsburgh Medical School. My brother is a mathematician at the Jet Propulsion Lab at Caltech. And so I tell you this not to brag, because these aren't my accomplishments, they're theirs, but to tell you the kind of neuroses that I was inflicted with growing up in that kind of a household. Our dinner conversations were generally very difficult for me, because no matter what we were talking about, I knew the least. And no matter what topic I brought up, they had more things to say about it than I did. And typically, as I began to take an interest in economics, I quickly became the black sheep of the family, because obviously, from their perspective, economics was not a science. You know, and I wish Gene were here today, because it's been used, his Nobel Prize has been used as proof that economics is not a science, because in what science could you award 2 Nobel Prizes in the same year to two people who say the exact opposite things, right? Schiller and Fama. And so that's the environment that I grew up, talking about science, math, and engineering, and how economics relates. Now, over the years, I've developed, I think, a number of good arguments. And so what I'd like to start with is science versus engineering, generically. What's the difference between the two? Now, here at MIT, we actually worry about different kinds of engineering, but I'm going to focus much more broadly on all forms of engineering. I learned that there were different forms of engineering when I first got to MIT, because one of the faculty told me a story. I don't know if it was really true or it's just apocryphal. He said that there were some faculty members that had a little too much to drink at a dinner party one night, and they started debating which kind of an engineer God is. And So the electrical engineer said, well, obviously God is an electrical engineer, because if you look at the human body and the brain, there are all these electrical connections, and that's, clearly a sign. Then the mechanical engineer said, no, God is a mechanical engineer because there are all these joints and muscles and the pulley system. That's what God does. And finally, the civil engineers piped up and said, no, God is a civil engineer, because who else would run a toxic waste pipeline through a recreational area? And so that's the kind of mentality that we have here at MIT. But if we just think about engineering generically and ask the question, what's the difference? You actually come up with some fairly obvious distinctions. Scientists want to understand things. Engineers want to build things. Scientists observe the world. Engineers seek to change the world. Scientists tend to be very theoretical. Engineers tend to be more practical. Scientists embrace ambiguity, whereas engineers are really frustrated by it. They want things to be very clearly defined, sorted out. And finally, engineers, they work hard, and scientists, they work free. So when you go down the list, a theme emerges. And the theme is that science is about understanding. It's a body of knowledge that provides some beautiful results about the underlying structure of things, whereas engineers take that underlying structure and they do stuff with it. But I want to make a different argument today. I want to change the definition of science and engineering to the following proposition. I believe that a body of knowledge only becomes a science when it is associated with the field of engineering that emerges to accompany it. I don't believe that you can call a body of knowledge science until and unless it's useful. And that's what engineering is. So yesterday, we talked about the beginning of finance science as Harry Markowitz. But I argue that Markowitz was also part of financial engineering the moment that Bar Rosenberg introduced the Barra model to the industry and took those ideas and said, you know what? You can actually use it to construct a portfolio. Because before that moment happened, it was just a bunch of math. And so this theme about science and engineering, I want to take through the rest of my talk and show how Bob has actually been able to do both. There are many scientists that are not engineers, and there are many engineers that aren't scientists. There are a very few who can do both, and when they do, they change the world. Now, we already know that Bob is a scientist. Paul Samuelson said as much. Paul Samuelson called Bob the Isaac Newton of finance. So clearly, finance science is one of Bob's accomplishments. By the way, Isaac Newton happened to also get involved in finance. I don't know how many of you realize, but he was the Chancellor of the Exchequer of the UK for a while, and he also speculated. He made a lot of money in the stock market. He lost all of it, though. He actually ended up becoming financially destitute because of the South Sea bubble. So, in fact, he lamented how difficult finance was, and he wished it was a lot easier, like physics. And I agree. So the theme of my talk is Bob Merton as an engineer. Well, that argument could actually be pretty easily made if you just look at Bob's background. Columbia Bachelor of Science from the School of Engineering and Applied Sciences, not the School of Social Sciences or the School of Science. And his degree was in engineering math, went to Caltech, got a master's degree in applied math, and then went on to get his PhD here. So just looking at his background, one could make the argument that he's an engineer, but I think that's a cop-out. I want to focus on specific examples from Bob's career. And I'm going to use 4 examples. There are many of them, but the examples that I want to give you are from his teaching, from research methodology, from derivative pricing, and finally from some of the practical things that Bob has been involved in. Now, Zvi told all of the speakers, including me, no math. And since I'm going to be talking about Bob's research methodology, there will be math. So please be prepared for that. I'm going to start with Bob as a teacher and tell you a little bit about how I got interested in finance. So I mentioned my science background from my family, and I went to high school, Bronx High School of Science in New York City, and then was fully prepared as an undergraduate to major in math, physics, or biology. Those are the three areas that I was most interested in. And it was only because I happened to take an economics class that was required to fulfill my distributional requirements that I got interested in economics and took a few more courses and got hooked. Some great teachers, Saul Levmore, Sharon Oster, Herb Scarf, and just really became enthralled with the idea of being able to use mathematical equations to predict human behavior. I'd grown up in the tradition of the Isaac Asimov Foundation trilogy, and I thought, gee, this could really be done with economics. So I went to graduate school at Harvard, and after the first semester, I was so discouraged about economics that I decided that I was going to apply to law school and just, give up the field because the first semester was a really bad semester. We had, first of all, pretty bad teaching. At the time, the faculty members at Harvard in the economics department, the key ones were on leave. Ken Arrow went back to Stanford. They didn't have somebody to teach graduate micro, so they induced a faculty who was about to retire to do so. It was a very difficult time for the economics department. But what really got me frustrated is that all of the models that we were taught in that first semester of my first year, they were the same models that I learned as an undergraduate. And while it was interesting, it was no more real than I was expecting. I thought that we would actually learn more sophisticated models that were closer to actual economic practice. That wasn't the case. So at the end of the fall of 1980, I started filling out my law school applications. I submitted my registration to take the LSATs. And a high school classmate of mine who was a senior at MIT, Li Ching Chow, she and I were classmates in Bronx Science, but because I had graduated a year early from undergrad, I was a first-year grad student here at Harvard, and she was a senior at MIT, majoring in management. She said, you really ought to take this course taught by a pretty interesting faculty member, and the course is 15415, Introduction to Finance. And actually, I think it was called Finance Theory at the time. Now it's like Mission Critical Finance, but back then it was just Finance Theory. And I'd never heard of the faculty member, some guy named Merton. But she said, it's a really interesting course. I think you would like it in particular because you like math, you like applications. This would be an interesting course to take. And so I took the course. And this is the syllabus from that course. And after the first 2 weeks, I decided this is what I want to do. And it was quite an astonishing transformation that I'll have to tell you in stages exactly what I saw. The first page of those lecture notes and the first class that we had was this diagram. Now, those of you who took the course, you'll recognize the diagram, but I decided that I was going to use it when I teach 415, so this is what the diagram looks like now. The magic of PowerPoint. But actually, I prefer this one because this was the first time that anybody ever showed me what the economy looked like from a systems perspective. I had taken graduate level general equilibrium theory, graduate micro, graduate macro, and in no course that I'd ever taken until 415 did anybody say, this is what we're studying, and this is how all the parts are connected. And now, let's go in and look at each of the parts and try to understand how it works. It was transformational. Now, it also helped that I had two fantastic TAs, Bob Ariel and Saman Majd, for that course. And so the subject for me just came alive. I was fascinated. And That was not the only thing that got me hooked, obviously. I took all of the courses that Bob taught, and unfortunately Stu Myers was on leave, so I didn't get to take any classes with Stu, but Rick Ruback was there. I took Fisher Black's courses. It was just absolutely fascinating. And I want to show you another flowchart diagram that came out of a course 15433 that Bob taught in capital markets. So you can't see this from back there, but this is a slide or a page from the lecture notes that describes the organizational structure for portfolio management. Now in 415, we went through the basics of mean variance optimization. 433, we actually dug into the details of mean variance optimization as well as dynamic programming. We got into some really complicated mathematical stuff. And I had to take a graduate course in stochastic control theory just to be able to understand the things that Bob was asking us to read in class. But this diagram, this convinced me that I'd made the right choice in deciding to focus on finance. Because for the first time, I saw in one slide, one page, one diagram, how all of finance science could be made practical. The different boxes are how you would structure a portfolio management company. You've got active portfolio management, passive portfolio management, super efficient portfolio construction. Today, that might sound like a buzzword, but in 1982, when I took the course, super efficient portfolio construction was based upon work of Traynor and Black on if you found a stock with a non-zero alpha, what should you do to combine it with a passive portfolio to maximize the gains from that alpha? There was science behind this, but this is engineering. And so I was just completely blown away by this. And the more I thought about it, the more I came to a really interesting realization that I suspect even now many of you may not be fully aware of about Bob's work. And it has to do with what you think the most important component is in this diagram. Now, many of you are in the asset management industry, so you know these components better than I do. If you had to say what the most important part of this diagram is, what would that be? Would it be the active part, passive, macro analysts, beta analysts, monitoring? Well, for me, the most important part of the diagram is not the boxes. It's the arrows. It's how all of these pieces fit together and flow. It's the dynamics. And that's an aspect of Bob's work that it took me a while to fully understand. I knew when I was in his classes, something was different about this guy and about this work. At first, I thought it was just the subject matter, but then I heard lectures by other financial economists, and they were not the same. Something was different. And I realized that it is the arrows. It's all about the arrows. It's about the dynamics. Now, most of you know that in economics, we're devoted to this notion of equilibrium, the idea that everything is in balance. Supply equals demand. And I spent a lot of time as an undergraduate and my first year of grad school studying general equilibrium, which is basically everything is in balance. All the markets across all the various different industries, at a point in time, everything is in equilibrium. And the fact is that when you look at the real world, virtually nothing is in equilibrium. Equilibrium is essentially static. It's a snapshot. Right now, things are in balance. Now, economists have tried to make it dynamic, like dynamic equilibria, basically going from one equilibrium to the next. But that's a very cheap way of studying dynamics. And when you see dynamics, you understand how important it is, how difficult it is to model. But that's how things work in the real world. Exactly. So, in order for me to talk about dynamics, I have to get to my second topic, which is research methodology, and in particular, the Ito calculus. That's been mentioned several times. So I'm actually going to talk about Ito calculus. I'm going to do a little Ito calculus right now. And you're going to do it with me. So first of all, this is a book on the left that was published in 1964 by two mathematicians, Kiyoshi Ito, Japanese mathematician, the University of Kyoto, and Henry P. McKean, who actually spent some time here at MIT and collaborated with Paul Samuelson, but spent most of his career after that at the Courant Institute at NYU. The two of them came up with a generalization of calculus to apply to random variables, and not just random variables, but sequences of random variables over time, which is particularly important for finance because stock markets, bond markets, they are sequences of random variables over time. Now, in order for me to describe to you the magnitude of the contributions and then Bob's contributions, I need to describe to you what stochastic calculus is. But in order to do that, I need to describe to you what calculus is, since some of you may not be familiar with that. So I'm going to describe to you some of the ideas that were first described to me in a paper that Bob wrote in 1971, Optimal Consumption Portfolio Rules and a Continuous Time Model. This is a remarkable paper for a variety of reasons. It's a technological tour de force. And it took me probably a year to get through this paper in grad school, and I had to take that course in stochastic control theory to really get inside this and understand it. And I'm not sure I really do, even to this day. I'm sure there are subtleties that I don't fully appreciate. But this paper was probably the first that introduced stochastic calculus in a serious way to the economics profession. Bob had written a paper in '69 on applying these ideas to growth models and appendix to some of Samuelson's work. But this paper, in my view, is the first complete exposition. And by complete, I mean section 2 was a digression on Ito processes. So it took you by the hand, a rather quickly paced walk by the hand, I should say, through some of the mathematics. And one of the footnotes, it took me 3 months to actually understand this footnote here, footnote 7. Warning, derivatives and integrals of functions of Brownian motion are similar to but different from the rules for deterministic differentials and integrals, for example, blah, 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 Stratanovich, blah, blah, blah. So it was an important footnote. And one of the things about Bob's work, if you haven't already figured it out, is that there are gems, diamonds that are buried in his footnotes. And even though it'll take you months and perhaps years to go through them, it's worth it. So I want to explain a little bit about this footnote because it's actually important. But to do that, I have to tell you a little bit about calculus. So calculus, as most of you probably know, was invented by Isaac Newton and Richard Leibniz. And it was invented as a set of mathematical tools to do certain computations, computations that would be difficult to do any other way. So one computation is, see that curve up there? Calculate the area under the curve. Now, we know how to calculate areas for things like rectangles, triangles. Triangles, 1/2 base times height. A rectangle, base times height. But how do you calculate the area of that weird-looking thing? Even if I gave you the formula for the curve, it's not obvious how to do that. And so the way calculus works is, let's start by approximating the area under the curve by a bunch of rectangles. And we'll put the rectangles at various different spacings across this curve. And we know how to calculate the area of those rectangles. And so if we calculate the areas of the rectangles, that's an approximation to the curve. And if we put more and more rectangles that are thinner and thinner, they get to look more and more like that curve. And so eventually, if we take the limit as we take an infinite number of these rectangles, we will actually get a perfect approximation to the area under the curve. So that's regular calculus. Now imagine if that curve is a random variable, and you begin to understand what Ito and McKean did. They came up with a method for calculating these kinds of quantities for random variables. And in order to do that, you need to make a decision. You need to make a decision on how to calculate the areas of those rectangles. Now, the way to do that, we all know it's base times height, right? But when you're approximating the function with these rectangles, you have to choose the point of the function at which you're doing the approximation. So let's just take a look at that one rectangle right there. We're going to use base times height, where the height is determined by the height of that curve, right? And so the height is going to be the function evaluated at the midpoint of that rectangle. That's how we calculate the height. We take the midpoint. But we could have chosen a different point. We could have chosen, say, the left endpoint of that interval, and we'd get a shorter rectangle as a result if we had done that. So in the expression that Ito and McKean used to create the stochastic integral, what they did was to use the left endpoint, not the middle, as most other calculus approximations would do. Now, why did they do that? Well, I'll have to tell you in a minute. But before I tell you that, you should know that there's an alternative to the Ito calculus, and that's what Merton was getting at in footnote 7 of his 1971 paper. The other way of calculating this integral is to use that midpoint, and that's what the Stratanovich integral is. Now, the difference between the Ito integral and the Stratanovich integral can be seen a little bit more clearly when you look at the differential version. I have to explain what that is now. The calculus is about adding up these boxes in order to calculate the area under the curve. But the flip side of calculus is to be able to understand the rate of change of that area under the curve. And for that, we can actually look at the differential. It's the inverse operation of adding up. It's sort of like taking differences and seeing how quickly things change. It's about dynamics. And so when we take a look at the differential version of the Ito calculus, that first formula says if you've got a function and you want to know how that function changes over a little bit of an interval, the formula for how to calculate that change is the top. And you won't know this unless you've done calculus before, but it turns out that if you have done calculus, the Ito formula looks different. It's got an extra third term that doesn't belong there when you're looking at deterministic kinds of functions. The Stratanovich integral, where you define the boxes by the midpoint instead of the left endpoint, it turns out that that does look like calculus. And physicists use this Stratanovich integral all the time. In fact, they prefer it because it doesn't have that annoying extra third term. So who cares? Why am I telling you all of this? Well, for one, Bob cares. In that same 1971 article, section 3 describes why the left endpoint is actually important in a section titled Asset Price Dynamics and the Budget Equation. And you might be thinking about that and saying, wow, that sounds really boring. It's not. This is one of the most important sections in one of the most important papers in finance. Because in this section, Bob actually shows how you define and derive the dynamics of how your wealth changes over time. And for those of you who look at your portfolios, you are doing the same thing that Bob does in this section, which is, how is my wealth changing over time? So in this very dense section, he derives the budget equation, for an individual trying to optimize his or her consumption and portfolio holdings. How is the wealth changing over time? And he does this initially in discrete time, and he gets this equation up here, which is the dynamics of your wealth. This says that your wealth at time t plus h is equal to your holdings of securities, the number of shares at time t, multiplied by the price at time t plus h. Now, this might seem like really minor accounting to you, but it turns out that this is an absolutely critical piece of the derivation that uses the left endpoint of the Ito integral because you see, in the Ito calculus, the horizontal axis is time. And if you use the left endpoint, what that's telling you is that you're making decisions and making choices based upon information that you have at time t for the future. Whereas the Stratanovich integral implicitly is assuming that at time t, when you make a decision, you're using information at time t plus h over 2 in the future. In other words, you're using information that you don't have. And that's a no-no. If you were able to do that, you would get tremendous arbitrage opportunities that really don't exist. Pretty important idea, right? Now, you might think that this is still mathematical mumbo-jumbo and this is not something that affects you. I guarantee you that most of you, if you were asked to calculate the profit of a trading strategy, simple equities trading strategy, that even the academics in this room, if I asked you to calculate a P&L, a profit and loss, you would get it wrong. Because typically, when academics calculate the return of a trading strategy, they would calculate the return that we get from the CRISP data, and they would multiply it by the weights as of a given day. That's actually assuming that you know the future. And it's not surprising that many academics, when they calculate strategies, they get tremendously profitable trades. When you actually take this into account, magically the profits disappear. So I only appreciated the depth of this section after I made that mistake and calculated trading strategies that were incredibly profitable. And I realized that when Bob did this, he actually knew how to calculate P&L. Now, how did he know this? It's because as an undergraduate and as a grad student, he traded. He actually calculated his own P&L. So this is Bob the financial engineer. As dense and as esoteric as this mathematics is, there's engineering here. Now, let me talk about the third topic, which is derivatives. This is something that has been talked about at length yesterday and today, so I won't belabor the point. Clearly, the Black-Scholes-Merton formula, this is the notes from 433. It was a breakthrough that Fisher-Black, Myron-Scholes, and Bob collectively achieved. Really stunning. But I want to make a different argument again. I want to argue that the work that Bob did in derivatives, that was the beginning, the real epicenter of financial engineering, in a way that was different than what Myron and Fisher envisioned. Now, Myron is here, so he can speak for Black and Scholes, but the reason that I say this is I actually presented some related work at Goldman Sachs, and Fisher was in the audience, and so he made some interesting remarks that I'll share with you, and then you'll see why it is that I'm differentiating between the Black-Scholes perspective, which may be different from the Scholes perspective, and the Merton perspective. So I'm going to go back to the paper that Fisher and Myron published in '73, Pricing of Options and Corporate Liabilities. In this paper, there's also an interesting footnote. Footnote 3. Footnote 3 says, this was pointed out to us by Robert Merton. What was it that was pointed out by Robert Merton that Fisher and Myron felt compelled to annotate in this footnote? Well, it was this. As the variables x and t change, the number of options to be sold short to create a hedge position with one share of stock changes. If the hedge is maintained continuously, then the approximations mentioned above become exact, and the return on the hedge position is completely independent of the change in the value of the stock. In fact, the return on the hedge position becomes certain. What Myron and Fisher did was to show that you can create a portfolio of stocks and bonds and options that collectively had no systematic risk, and therefore it had to earn the risk-free rate, and that gave the famous Black-Scholes PDE. And they got the formula, and that's why it's the Black-Scholes-Merton formula as opposed to the Merton-Black-Scholes formula. But what Bob showed is that not only can you get rid of the systematic risk, you can get rid of all the risk if you trade continuously in time using the Ito calculus. And to me, as somebody who is thinking about engineering, that makes all the difference. Now, when I presented a paper co-authored with Leonid Kogan on dynamic trading strategies using dynamic programming, we presented it at Goldman. Fisher was in the audience. And we said that, Fisher, this is really an extension of the work that was done by Black, Scholes, and Merton using the delta hedging. And Fisher said, I never liked the delta hedging argument. And I said, but you can do this without the CAP-M. And he says, I know, but I like the CAP-M. And so I actually believe the CAP-M because it's an equilibrium model. Now we go back to this argument of equilibriums versus dynamics. I'm in the camp that I don't believe in equilibrium, but that's a separate issue. So this, to me, is the beginning of financial engineering. And I wish, again, Gene were here, because I would cite Gene as an example of why continuous time trading is so important. In 1992, we all learned that the CAP-M was dead, right? And so if you believe that the Black-Scholes formula relies on the CAP-M, and in fact it doesn't, but if you believe that it did, then you would be sadly disappointed by this news. So going back again to the 433 notes, there's a passage in here that I just found stunning. And this is where I call this the beginning of financial engineering. This passage. We have created a security in quotes. We have created a security with an identical payoff structure to the option. The investor always has the right to manufacture an option if it is cheaper. To manufacture an option. You can make this thing. You can build it. And that's the key to the engineering part. The science says this is what the price ought to be. The science says this is how the pricing works. But the continuous trading, the delta hedging, that shows you how to build it. And it was built in spades. 4 multi-trillion-dollar industries that are based on the idea that you can build it. If you don't have it, if it doesn't exist, no problem, we'll make it for you. And by the way, we'll charge you a little bit for that, for the privilege. Exchange-traded derivatives is one example, of course, but OTC derivatives, in 2018, there were $544 trillion of notional OTC derivatives out there. 544 trillion. Now, people say, well, that number is ridiculous. That's just notional. You should net it out. And yes, if you net it out, the net exposure is maybe only 9 trillion. But you know what? The number 544 trillion, that number is not to be trifled with, because that notional means that there are people out there that are looking at that number, because even though 2 counterparties may net out, each of the counterparties do have that notional exposure, and they're looking at that, managing it, and wanting to understand what the risks are. Black and Scholes and Merton have provided us with the means of understanding that. So this is financial engineering. We can build it. Now, the last thing I'm going to turn to is practice. And it's pretty obvious that Black, Scholes, and Merton have transformed many industries now with the ability to manufacture these securities. And in fact, an industry organization emerged over the course of the years that used to be called the International Association of Financial Engineers, formerly the IAFE, now called the International Association of Quantitative Finance. It's unfortunate, but they ultimately bowed to the pressure of the negative press that's associated with the term financial engineering. But they still use the term the Financial Engineer of the Year, and last year Francis Longstaff was honored to be the Financial Engineer of that year. They started awarding this in 1993. Who do you think the first Financial Engineer of the Year was? Bob Merton. So I rest my case for the title of my talk, First Financial Engineer. However, sorry, I had to do some sound effects because I knew we had to wake you up for the last session. However, we know that people now think of derivatives as financial weapons of mass destruction. And I know that this quote from Warren Buffett was taken out of context. Buffett uses derivatives all the time. But he was serious and sincere and thoughtful when he wrote this in his annual report, because there are certain contexts where financial derivatives are extraordinarily dangerous and could have catastrophic consequences. So if derivatives are, in fact, financial weapons of mass destruction, and there's a case to be made, and I'm going to make it here, well, then I would argue that that means that Fisher, Myron, and Bob are the equivalent of Albert Einstein, right? But before I get to that, I want to mention that the critique of financial engineering, that critique actually has spread to none other than the grandfather of modern quantitative finance, Paul Samuelson. Samuelson was quoted in a PBS special as saying, fiendish Frankenstein monsters of financial engineering have been created, a lot of them at MIT, some of them by people like me. I was shocked when I read this and I heard about this. And I never got a chance to talk to Samuelson about this. I obviously disagree. And I'll have a few more things to say about this. But let me now turn to the analogy of financial weapons of mass destruction and the idea that, in fact, Bob, Myron, and Fisher are the Albert Einstein of finance. And I'm going to take this analogy quite seriously and think about this. So first of all, can we make a case that Einstein was an engineer? Well, you probably all know that he got his start after his PhD in physics as a patent clerk. For 7 years, from 1902 to 1909, he worked in the patent office in Switzerland, in Bern. And he could not get a job as an assistant professor. His work was not particularly well thought of. He graduated and he had some fans, but he was by no means a wonderkin that set the field on fire. So for 7 years, he basically worked examining patents. In the middle of those 7 years, he produced a number of papers. In particular, in 1905, his miracle year, he produced 4 amazing articles on the photoelectric effect, on Brownian motion, on special relativity, on E equal mc squared. All of those was while he was a patent clerk, figuring out other people's inventions. So right away, this actually reminds me a bit about Bob in the sense that, I don't know if there was 1 year that was the annus mirabilis, but there were probably 2 or 3 years that came pretty close. But I want to continue on with this notion of Einstein as the engineer and let you in on a secret that most people don't know. Einstein was actually an inventor. He actually held a number of patents. And in particular, an article that was written about his patents, these are the patents that he had filed jointly with a colleague physicist named Leo Szilard for a new method of refrigeration. You see, refrigeration technology was relatively new in those days, and a number of deaths occurred because the refrigerant was poisonous. They used things like ammonia, sulfur dioxide, methyl chloride, and in 1926, a Berlin family, including children, all of them died because the refrigerant leaked in the evening, killed them all. So Einstein was very affected by this. So he and Szilard came up with a patent for a refrigerator that had no moving parts. An amazing invention. Had a hard time getting it licensed, and ultimately they did sell the patent to a company in the UX called Electrolux, and they sold it for about what is today $10,000. But it was designed to deal with a problem. And that theme comes over and over again in engineering. The idea is that because we're dealing with real systems, we're dealing with dynamics, not simple static problems. It's far too complex. We can't answer all of the questions, so we're going to run into problems. Space shuttle explosions, nuclear meltdowns, train wrecks. And so the key is for us as engineers to learn from those mistakes and to improve. Now, this is a theme of a well-known engineer by the name of Henry Petrosky. I thank Zvi for introducing me to his work. Petrosky is an expert on detecting failure and understanding how failure informs engineering. And he argues that part of engineering, an important part, is experimentation and understanding failure. And one of the wonderful examples that he gives is of the Tacoma Narrows Bridge in 1940. This bridge opened on July 1st, and almost right away, it was pretty clear that the bridge was not well designed. Dynamics, it's all about the dynamics. And in November of 1940, the bridge collapsed. Now, this bridge was the third longest suspension bridge at the time, 2,800 feet from span to span. And it turns out that we figured out the problem with this, and now there are many other bridges that work a lot better. This is a bridge in Kobe, Japan, was opened in 1998. This is 6,800 feet, twice as long as the Tacoma Narrows Bridge, not a single problem. That's part of engineering, figuring out what went wrong. Another part of engineering is actually taking your knowledge and applying it to important issues. So I'm going to come back to weapons of mass destruction. Do you know why we have weapons of mass destruction? Well, in 1939, Einstein wrote a letter to President Roosevelt, co-authored with Leo Szilard. This is the letter. And let me read to you the letter. In the course of the last 4 months, it has been made probable, through the work of Joliot in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. 1939. And the letter goes on to point out something that when I read this, I found incredibly chilling. And this ultimately motivated the United States to launch the Manhattan Project. I understand that Germany has stopped the sale of uranium from the Czechoslovakian mines, which she has taken over. That she should have taken such early action might perhaps be understood on the ground that the son of the German Undersecretary of State, von Weizsäcker, is attached to the Kaiser Wilhelm Institute in Berlin, where some of the American work on uranium is now being repeated. The Kaiser Wilhelm Institute is the most prestigious physics research institute in Germany. Einstein was the director of that institute from 1917 to 1933. And in 1939, this institute had started trying to replicate some of the experiments that Szilard, and others in the United States were doing on splitting the atom. This is why Einstein wrote the letter to the president. This is why we have weapons of mass destruction. And fortunately for us, it succeeded. Otherwise, this conference would be probably held in German right now. So sometimes engineering requires action and policy work. And Bob has done this as well. In the post-financial crisis, Bob has written a number of research papers, a couple of which I've had the privilege of working on with him, on how to analyze systemic risks so we can measure and monitor and hopefully deal with future financial risks. This is a paper with Dale Gray and others, another paper on how the mortgage crisis could actually be the result of just complete happenstance in that the perfect storm of various different financial engineering aspects come to roost. And the existence of the new agency, the Office of the Financial Research, the agency charged with monitoring and measuring, that was actually due to a letter that Bob wrote, along with other finance Nobel laureates and Alan Mendelowitz and John Leichty, to Senator Jack Reed, that basically got this organization stood up. And if that weren't enough, in the effort that Lars Hansen and I have started on the macro financial modeling group, where we're trying to get these techniques out to graduate students and other young scholars, Bob has been a tireless participant of that effort, speaking at these conferences, participating in our organizational activities, and getting the word to the next generation that they need to think about systemic risk more directly. And obviously, you heard about what Bob and Arun are doing in selfies. This work could actually be the most important work that Bob has ever done in terms of affecting literally hundreds of millions and billions of lives. And he's still doing it now. So let me wrap up since I'm out of time, and I'm sure you're all hungry, ready to go to lunch. I want to wrap up with some bold statements. Human civilization has had a remarkable run for the last 100,000 years. That run has been largely the result of technological innovations: agricultural technology, medical technology, manufacturing technology, most recently information technology. All of those technologies have a theme in common, and that is they need money. They need financing, and as a result, they all need financial technology. Now, we're facing some of the biggest challenges we've ever faced as a civilization: climate change, flu pandemics, Alzheimer's, cancer, the eventual exhaustion of fossil fuels. And I don't know whether we're going to make it for the next 100,000 years. But I know one thing for sure. I know that the technologies that we will develop to deal with these challenges, they will require financial engineering. And that's why I'm so grateful that we have right here at MIT inspiration and motivation and the expertise of the very first financial engineer. Thank you, Bob.